Recently, Micronova, the company that developed the Mercury FPGA, has released a daughter board that can be used with the Mercury to help in the development of VHDL systems. This board is called the Baseboard, and is currently available on their website for $19. In this video, I'll talk about the baseboard, what it offers, and give a short demonstration using some of the peripherals. The baseboard has two 32-pin female headers in the center to accommodate the Mercury board. When the board is inserted, you also have two more 32-pin female headers along the edge that breaks out all the pins of the Mercury. You can see that I have a rough solder job done here to accommodate the pins that I accidentally broke off. Now that we have the board in place, let's go around the baseboard and look at what is offered. Starting from the top, we can find the 4-digit 7-segment display. This is a typical 7-segment setup, where there are 4 enable lines that can disable or enable any specific digit. These enable lines are active low, meaning that if you want the least significant digit active, you will set the 4 lines to hex E, or 1110 in binary. Then there are the 8 wires that control the individual segments in the displays. The individual segments also include the decimal point in the 8 wires. These lines are also active low. Setting a line low will allow the corresponding segment to glow. In the demo later, I will provide a driver to operate the 7-segment display. Moving to the right is a VGA port that can be used to control a computer monitor. Here you have a digital to analog conversion for each of the red, green, and blue colors. Let's assume that you are using digital logic. Since there are 8 lines for colors, you have 8-bit color, with the ability to create 256 different colors. If you wish to get more colors, you can optionally pulse width modulate these lines to get a wide array of color values. You also have the horizontal and vertical sync signals as well. On the bottom edge of the board is an array of 8 two-way switches. When the switch is down, it will weak pull the corresponding pin on the FPGA to ground. When the switch is in the up position, it will do a weak pull up in the same pin. These pins can also be used for additional GPIO if needed, with a configurable pull up or pull down resistor. Next is the array of 4 momentary buttons that are wired to be active high. By default, it provides a weak pull to ground. In the corner is an interesting collection of analog sensors that are wired directly into the channels of the Mercury's onboard analog to digital converter. Here there is a potentiometer, a photoresistor, and a temperature sensor that are hooked up to channels 4, 3, and 2 respectively. An easy way to interface to these is to go onto Micronova's website. In the resources section, there is a VHDL module to interface to the onboard ADC. Later in the video, I'll show a small demonstration making use of the VHDL module and the potentiometer. On the left side of the board, we will find the audio in and audio out TRS female jacks. These audio jacks support stereo sound and have pre-built filters for you. Starting with the audio in jack, you get these 2 DC blocking capacitors. The signal then reaches these op amps configured as buffers. Since these op amps ideally have an infinite impedance, the signal will be driven by the op amp and not by the audio in application. Then you have a simple RC low-pass filter. The signals are connected to channels 1 and 2 on the analog to digital converter. For audio out, you almost have the opposite. First an RC low-pass filter, then you get a non-inverting amp with a gain of 2, followed by another set of DC blocking capacitors. Next is the PS2 port, which can be used to interface to an old computer keyboard or mouse. You also have a jumper that provides the option if you want your device to be supplied by 3.3 volts or 5 volts. Then you have the peripheral module connector, also called Pmod. This gives you the ability to expand or simply use it for more GPIO, but it can be used if you're interested in adding some cool hardware to your board. Probably the best Pmod supplier is Digilent, although it can be expensive. Some of the coolest Pmod extensions are the GPS, Wi-Fi, and OLED ones. See the link in the description to see all the Pmods that Digilent offers. On the baseboard, you also have a voltage select jumper for the Pmod hardware. And lastly, there's a JTAG port interface, if you're interested in trying your hand with that. I've been playing with this board for a little bit now, and I really can't find anything to complain about. Like the Mercury itself, the layout on the board is tight and has a small footprint. I'm actually really surprised that they're only selling it for $19, so it's a great way to add additional peripherals for development. For demonstration purposes, I'm just going to do a simple application where I measure the potentiometer and drive the 7 segments with the value of the sensor. So let's create a top level diagram for the VHDL application that we're going to use. You can see here that in the past I had the gray box representing the Xilinx Spartan 3A FPGA, which I'm going to use to write the VHDL application to. Surrounding that is the Mercury board, and then when the Mercury board is mounted onto the Mercury baseboard, we add this additional layer. This additional layer is represented by the red box. Now the peripherals that we're going to use for this project is going to be the onboard button, going to be used for resets, the onboard clock, the analog to digital converter IC, connected to the potentiometer on the baseboard, and finally the 4-digit 7-segment display mounted on the baseboard for an output. Now I apologize in advance because I'm going to move very quickly here. The reason being is that I plan on covering the concepts here in my next video, FPGA's Lesson 3. Also, this is intended to be a product demonstration video and not a concept introduction video. So with that said, here I added the module, the Mercury ADC supplied by Micronova. This is the module that I'm going to use to interface to the ADC to read the potentiometer. The Mercury ADC communicates through SPI to the analog to digital converter IC. So when you download this Mercury ADC, what you're going to want to do is connect the SPI lines to the pins on the FPGA to the ADC. It also has two outputs. D-out is going to give the 10-bit reading from the ADC, and out-val is going to pulse high when you receive a new value from the ADC. This trigger line acts as a signal method to tell the Mercury ADC that you want to sample from the analog to digital converter. Now, according to Micronova, the fastest that you can sample here is 3.6 megahertz, provided that you're connected to 5 volts. This diff-n input is used for if you want differential sampling or single-ended sampling. And here we're just going to be using a single-ended sampling, so I'm just going to write this just right to 1, basically. And then channel is pretty obvious. It's just a 3-bit signal that dictates what channel the ADC do you want to read from. Now, since the potentiometer is hooked up to channel 4, I'm just going to wire this up to 4. So since I can only sample this Mercury ADC at a certain rate, I can't just hook up the clock 50 megahertz to it. So I'm going to create a module that's going to slow down the clock in such a way to trigger this ADC at a consistent rate. However, slow enough so the Mercury ADC can successfully sample from the onboard ADC. For that, I'm just going to use a simple clock divider, which is going to be hooked up to clock and reset. And then the output will just be this clock signal, but divided by 512, or 2 to the 9th power. So that will be slow enough because, like I said before, the fastest you can sample is 3.6 megahertz, but 512 will divide that down to like approximately 100 kilohertz. So you're well below the highest rate that you can sample this at, but you're also definitely fast enough where the user can't see any lag between adjusting the potentiometer and the output the user sees. Now we need a way to get this D-out value onto the 7-segment displays. Well, it's D-out and out-val. Since this out-val pulses when a new value is retrieved from here, it's perfect application for a register. So here's my register that I'm going to add to the design. D-out will just wire straight into this data signal here, which is 10 bits long. And out-val will connect to the load signal on the register. The register also outputs 16 bits, but that's to interface to the quad 7-segment display driver that's going to go over here. What this register is going to do, it's going to take in the 10 bits of data coming from the Mercury ADC and then concatenate that. So this is going to just be the ADC 9 down to 0. So that's what the output of this is going to look like. This register also has clock and reset signals, but I left them out for simplicity. And to go from the register to the 7 segments, I created this quad 7-segment driver. So all you have to do for the driver is you just pass what value you want to be displayed here in hex, and it will display that value in hex. And it just needs to connect to the individual segments A to G, and also the enable lines. to multiplex through the digits. Now, as I said, this driver works in hex, so if you were to put in 1F2E into the input here, then you're going to display 1F2E on the output as well. So that was just my black box analysis of this module that I created. In my FPGA's lesson 3 video, I'm going to go over more of a white box analysis of how this was derived and show you how to make something kind of like this. So now that we have the top level all put together, I'm just going to go through the tedious task of executing all this in VHDL. So I created all the VHDL necessary to implement that top level. You can see that I have the register, the clock div 512, and my 7-segment driver that I made, and the Mercury ADC that I got from Micronova. Then I just made a simple top level of the whole thing. Micronova also supplies a special baseboard user constraints file that's to be used with their baseboard. And what's different with this UCF as opposed to their default one to use with the Mercury is that this one kind of abstracts the locations of the peripherals that are located on the baseboard. So you can just use easy names like A to G for the segments on the 7-seg displays and the enable lines, as opposed to using the Mercury UCF file, which would be pointing to specific I/O on the Mercury board. Now this one that I have here is a relic from a previous project where I X'd out a bunch of the locations so that way I could get rid of a bunch of warnings. So this baseboard that I have supplied here won't be the complete baseboard file, so make sure that you get this baseboard file from Micronova's website. As always, I'm going to have this entire project in a link in the description of this video so you can easily access all this and pick what you want. And also take care to make sure that you picked the right device, because Micronova supplies 2 different Mercury boards, and one is the 500A. And I have the 200 gate equivalent FPGA, which is why I have this one. So now I'm just going to generate the programming file. And now all I have to do is upload this to the board. I have the board plugged in, so just connect, go. So to adjust the potentiometer, it's a good idea to use a flathead screwdriver. Right now, the 7 segments are set to 0, and so I'll give it a turn in the counterclockwise direction. And so it's starting to increase. I'm trying to get one of the hex values. So A, B, C, D, E, F. So you can see the driver works. And if I go to the other extreme, I'm going to stop at 3FF, which makes sense because that's the maximum hex value for 10 bits, which again is a resolution that we're getting from the analog to digital converter. And again, this entire VHDL system is available in the link in the description. Be sure to also check out Micronova's website and check out their new baseboard. Now, I realize that this demonstration is a little lame, but that's because in my FPGA's lesson 3 video, I have something already made that uses this baseboard, and it's actually pretty cool in my opinion. I already had the lesson planned for that video created, so I still have to shoot the video, but hopefully we'll see that soon. Well, thanks for watching. This has been a product demonstration and review of Micronova's latest baseboard.